I'm going to talk about expanders and metric spaces in metric spaces. So, expanders, this talk just infinite family of constant degree graphs that have a uniformly bounded spectral gap. Spectral gap is just the difference between the first and the second eigenvalues in the adjacency matrix. Here I'm using normalized metric adjacency matrix after dividing by the degree. And we know that expander graph exists. This was first proved by Pinsker. It has many applications in computer science and in math. And in this talk, I'm going to describe, well, there is also applications for metric geometry, which I'm going to show you. And it all begins with the following inequality that is you see at the bottom of the slide that says that in any graph, basically any regular graph, if you take a mapping of the vertices into the real line, and now you take the average over all pairs of vertices, and you look on the distance on the line, distance squared, between the images of these two vertices. This is at most the average of the same quantity but over the edges of the graph times the reciprocal of the spectral gap. And this is actually very easy to derive. I'm not going to do it in this talk, but it's one line standard calculation. But here you already see that this inequality would be a session in this talk, and you see that this is actually characterization of the spectral gap. The spectral gap is just the supremum of the average over the edges, or the ratio between the average over the edges to the ratio of all pairs of vertices. So this is a metric inequality, right? You see distances here. So let's generalize it a little bit. Let's write this similar inequality, but now the mapping is not into the line, but into a Hilbert space. It turns out that you have the same inequality when you map the vertices into Hilbert space, and this is very easy to see. We know it for the line. So in Hilbert space, you can just take orthonormal bases, and for any such general mapping, you can look on the projection for each of the base elements. Each projection is just mapping into the line. You have this inequality on the line. You sum them up, and you get the norm.
Where is the spectral gap?
Okay, so this approximate inequality is just inequality up to constant factors, and this is expander. So we assume there is a uniform bound of the spectral gap. So this is just a constant, which depends on f, on the family of on the expander. This is one inequality, and we have a reverse inequality. The reverse inequality it just basically holds for any regular graph, and it also holds for any metric space. It's just an application of the triangle inequality. So if you combine these two inequalities in expander graphs, in expanders, you actually have an approximate equality. Okay, so this is you have average over all pairs, average over edges, and in expander graphs, they're roughly the same. They're approximate equal. So here is the first application of this approximate equality for non-embeddability. And it says that, well, this is the approximate equality that we saw before. Any mapping into Hilbert space, the average over all pairs and the average over edges is roughly the same. Now, this, if you think about it, it says that the metric, the shortest path metric on expanders is not compatible with the metric of Hilbert space. It cannot be embedded in Hilbert space. And why is that? Look at the shortest path metric on constant degree graph. This is expanders, right? In particular, the constant degree. most pair vertices in the graph metric are far away from each other, right? The distance between them, for each vertex, most of the other vertices are a distance order of log n from this vertex. So the left-hand side in the graph metric is something like log n squared, whereas the right-hand side is average over edges. The distance between endpoints of an edge in the graph metric is at most 1. So it didn't say the graph can have multiple edges and self-loop. So it's not exactly 1, but it's most 1. So this difference between, the fact that in the graph metric the average over all pairs tend to infinity with the size of the graph, whereas in any embedding into Hilbert says this average must be at the same, roughly the same as the average over the edges, means that you cannot embed the graph metric. And this was first observed by Linian, London, and Rabinovich for distortion, notion of embedding that's called distortion in L1. And then Matushik generalized it to any LP, embedding into LP when P is finite. And Gromov looked on different kinds of embeddings, and the same inequality shows that no embedding is impossible. Also in so-called coarse embedding. Application. So one application that LLR observed is, this is actually tightly, I mean, it implies an integrality gap for the linear, Layton-Rowley linear programming relaxation for the sparses cut. Gromov used it to build a counter example for in geometric group theory. So this is one application. Here's another application, more algorithmic by Bahum, Goldreich, and Schreibman. And it started with a question of INDIC. In this INDIC asks whether given endpoint metric space, can you estimate the average distance in a small number of distance squares, little o of n squared distance squaring? And the answer is yes. If you sample randomly linear number of pairs from the metric space, and you average them, you get with high probability 1 plus epsilon estimator. This is the work result of INDIC, and it was improved. The dependence on epsilon was improved by Bahum, Goldreich, and Schreibman. But BGS went further and asked a type of generalization question. They asked whether there exists a universal approximator. So universal D approximator is basically a specification of pairs of vertices such that no matter what metric you put on this point, if you average the pairs that you chose, you get a D approximator. So it turns out this is also possible. They show that there are universal approximators with n to the power of 1 plus 1 over d pairs or edges. And in general, this is also necessary. But in some classes of metric spaces, you can do better. So for example, in L2 and L1, they show that you can use only linear number of pairs. And the solution is quite simple. And it's the same approximate equality that I showed. This approximate equality says that if you take an expander on the points, the edges of the expander, you get approximate, you can average over the edges, and this is approximately the average over all pairs. I'm ignoring the power of 2 here. So you can think about averaging the square distance instead of the distance. And actually, BGS was a little bit, actually got even 1 plus epsilon approximation. Here you need to be a little bit more careful, and you should also use a good expander or Manor-Mendel graphs. But this won't be important in this talk. The point in both applications, the non-embeddability and this distance approximators, that actually makes sense beyond L1 and L2. You can ask yourself whether it works in other metric spaces. Obviously, we saw from the lower bound of BGS it cannot work for any metric space, but we can ask whether it works for other interesting metric spaces. And for this, I want to define a generalized or stronger notion of expander. So let's define the notion of gamma. Gamma would be just the supremum over all mappings. Gamma with respect to a metric space X, here is abstract metric space X, would be the supremum of the ratio that we talked about before, average over all pairs divided by the average over the edges. And now we look at distances in X, distances squared in this metric space X. And gamma, when the mapping is, when X is just the line, gamma is, as we saw before, basically the reciprocal, exactly the reciprocal of the spectral gap. So now we can define a stronger notion of expander. The expander with respect to a metric space X is just constant degree, a family of constant degree graphs in which the gamma is uniformly bounded from above. And the first observation is this terminology is legitimate in the sense that any expander with respect to, expander with respect to any metric space is also a classical expander. Why is that? So gamma, we want to bound from above gamma of G with respect to the line metric. And well, by Chigger inequality, we know that the reciprocal of the spectral gap is at most the reciprocal of the edge, normalized edge expansion squared. Now, if you think about it, what is edge expansion? In this terminology, is just, or the reciprocal of the edge expansion, in this terminology is just gamma with respect to the metric space of 2 points. This is an easy exercise. Now, the metric space, obviously, if X is non-trivial, the metric space that we care about is non-trivial, it contains more than 1 point, it contains more 2 points, so this, you can see from the definition of gamma that it must be larger. So if gamma with respect to X is bounded, uniformly bounded from infinity, then so is the reciprocal of the spectral gap of G. Okay, so this is a very simple observation. The next thing you can ask, well, is there an expander with respect to all metric spaces? And the answer is obviously no. We basically already said it in the beginning of the talk. If you look on a metric space, it contains all finite metric spaces, and there are such metric spaces, for example, L infinity. Then, in particular, it contains the metric of the graph that you want to calculate its gamma. And if you look on the identity embedding, you get again the same problem that we saw at the beginning of the talk. The average over all pairs is something that behave like log n over log d. Most of the distances behave like log n over log d, so the average over square distance is something like log n over log d squared, and the average over the edges is 1. So gamma is unbounded. So there is no constant degree expander with respect to L infinity, for example. What about ballast spaces? So as I said before, Matuszek essentially showed that for any expander is also expander with respect to LP when P is finite, and this was generalized, improved, sharpened by various peoples. There are no expander with respect to L infinity. So this is relatively easy cases. Now, people from some reason, in the recent years, people from geometric group theory started to talk about, they care about uniformly convex Banach spaces. Now, I'm not going to define it. It won't be important for this talk, but the nice story about it is it took some time until Lafog actually was able to construct expander with respect to this class of Banach spaces. We later gave a different construction, but the point in both construction is that it's not that we don't know whether any expander is expander with respect to this class of Banach spaces. We have two specific examples. And the question whether any expander is expander with respect to this, with respect to uniformly convex band space is actually an open and important in this, for that community. And it's open, and we don't know how to, we don't currently have any tools to solve it. But we can ask maybe simpler and more basic questions. Is there any metric space that can differentiate between different expanders? So is there a metric space such that there is one expander which is an expander with respect to this metric space and another expander which is not? And we can actually, for this question, we can actually answer. The answer is there are such metric spaces, and this is the main result of the work. I should have said this work is a joint work with Asaf Naor. This is our main result. So we construct a expander Z and a metric space X with the following property. First, Z is expander with respect to X. And second, X contains isometrically almost all three regular graphs. So it contains random three regular graph. What does it give us? First, it gives us the separations that I just said. So random three regular graph is almost surely an expander. So X contains many expanders, contains them isometrically. So this, as we saw before, these expanders cannot be expanded with respect to X, whereas Z is expanded with respect to X. And another algorithmic application is that Z is now a universal approximator for the class of random regular graphs, basically, random constant degree graphs, which should be useful at least in where random regular graphs are used. Sometimes they are used in networking, for example. So now we have a way to obliviously estimate average square distance on subset of networks that comes from random regular graphs. So this is a statement of the theorem, but maybe the main point here is that I think that the proof is more interesting than the statement itself. From the statement of the theorem, the theorem is a little bit exotic, I would say the least. But the proof has some new technique. So first of all, the graphs themselves, the expander that we use is a small variant of the zigzag expander of Reingold, Badhan, and Wigderson. The main novelty is in the analysis, where the way we analyze it, at least, is by we want to reason on random regular graph, on the metric of random regular graph. What we did, we take this one-dimensional object, the one-dimensional simplicial complex, and we embed it into two-dimensional metric space called the Euclidean cone. And this Euclidean cone turns out to have nice properties. In particular, what we're going to use, it has, roughly speaking, a non-positive curvature. And we can use this curvature to define a non-positive curvature to define martingales and write martingale inequalities on them, and you'll see in the and you see, I mean, how it plays out in the rest of the talk. So this is the statement. This is, I mean, just buzzwords about the proof. And now the details. You can go to sleep if you want to, but yeah. So what are RVW expanders? I'm not going to define the RVW expander. I don't have time for this, but they have three ingredients. They have a base graph. Base graph is just a graph with good spectral graph, a specific graph with good spectral graph. They use the power operation, taking power of graphs, and they use a zigzag product of graphs. And in this talk, I'm going to concentrate on the power operation. So what is power operation? You are given, in this setting, a d-regular graph. G to the power of s is a graph on the same set of vertices, and the edges are just walks of length s in the original graph in G. So this graph have a degree d to s, and the eigenvalues of this graph are just powers s of the eigenvalues of the original graph. In particular, the second eigenvalue in absolute value is power s of the second eigenvalue of the original graph. And in terms of gamma, what's going to happen is, in terms of gamma, if you do the simple calculation, simple estimation here, you see that gamma of g to the s behave like gamma of g divided by s, as long as it makes sense to behave like that. As long as gamma of g, as long as it's more than 1. So it's the maximum, it is at most the maximum between 1 and gamma of g divided by s, times 2. I ignore this constant. So you see what the power gives us. So the way that zigzag expander are constructed, they are constructed iteratively. The next graph in the family is constructed from the previous one. And the way to do it, we want to, so the power operation, what it does, it improves the gamma, it decreases the gamma at the cost of increasing the degree. And the zigzag product will counterbalance this, okay? But we are going to, as I said, concentrate on the power. And you see what happens here. We have this gamma which improves in the classical spectral gap, but now I want to talk about gamma in general metric spaces. Does it also improve? So it turns out it doesn't. So let me qualify it. And qualitatively, I mean, this is just a simple Gaussity argument. Gamma of g to the power of t tends to 1 when t tends to infinity. But for the application of the zigzag expander, we need more uniform control on the decay of gamma of g to the power of t. And it doesn't have to be gamma of g divided by t. It can be worse, but we need some uniform control. And there are examples of metric spaces, exotic metric spaces, that we don't know it for normed space, for example, but there are examples of exotic metric spaces for which the decay of gamma of g to the power of t as function of t is not good enough for the construction of expanders. But we don't care about general metric space in this talk. I care about random regular graphs. You can ask what happens in random regular graphs, and the answer is, as you can see, we don't know. We don't know whether it's good decay or not. What we're going to do is do something more complicated, which we know how to analyze. And this is, as I said before, we're going to embed this. We're going to embed the metric of the random regular graph in two-dimensional metric space called the Euclidean cone. So what is the Euclidean cone? So the easiest way to introduce it is to think of the Euclidean cone of the sphere. It's a way to get the Euclidean space out of the Euclidean sphere. So we have Euclidean sphere. We want to represent Euclidean space and contain it using the sphere. This is sometimes called spherical coordinate. It basically you take here x is a sphere, the sphere with, I should say, with the geodesic metric on it. With the geodesic metric is just the angle, the distance between 2 points is just the angle with respect to the origin. How do you represent the Euclidean space? You can just take the Cartesian product with the ray, infinite ray, and you also add the point 0, right? And how do you define the distances, the Euclidean distances in this space? This is according to the cosine formula that you see here. Okay. So this is the Euclidean cone of the sphere, just the Euclidean space. And you can generalize it to abstract metric space. Instead of the sphere, put an abstract metric space. There is one important caveat, and that is that we cannot, I mean, we need the distances to be less than pi, right? It doesn't make sense to think of this, of the Euclidean case. It doesn't make sense to have distances larger than pi. So how do we do? Just truncate the distances at pi and take the same formula, and this would be the Euclidean cone over abstract metric space. And one observation is that if the distances in X were all less than pi, if the diameter of X was less than pi, then the canonical embedding of X inside the cone is actually quite good embedding. The distortion is very small. Think about what happened in the sphere. In the sphere, the largest distance is pi, between two antipodal points. What is the Euclidean distance between them? 2, right? And this is actually, so you have distortion. It's not the same number, but the distortion is only, the contraction is only pi over 2, which is a relatively small number. And smaller distances have smaller contraction. So this is only distortion, it's what we call distortion of pi over 2, which is small constant, which, I mean, the list of our problems in terms of the constant that we get in this construction. So we just ignore it. And which means that if you take any bounded metric space, you can actually, if you first scale it down by its diameter, multiply the distances by pi over the diameter such that its diameter becomes pi, then it contains what we call B-Lifshitz, a copy of the original metric space, right? You can, any metric space, bounded metric space, you can squeeze it down and embed it into the cone over it. This is what written in the last point, and this would be important. So this is the cone over the metric space contain the metric space provided that we scale down by the diameter first. So this is what we're gonna do. We're gonna construct a cone over the random regular graph, and we're gonna prove that the expander, the zigzag expander, are actually expander with respect to the cone over the scaled version of the cone over the random regular graph. And this is actually a stronger result because, as I said before, this cone contains canonically the metric of the random regular graph. Why we are going to do it? We're going to do it because this cone has a nice property, which this cone has this property that's called cut zero, which I'm going to define in the next slide. And the nice thing about cut zero spaces, they have this decay property that we look for. Okay. So what are cut zero spaces? So why called cut? Okay, let's see first of all what is cut zero. So cut zero spaces are geodesic spaces, metric spaces in which if you take any 3 point, now any 3 point give you a triangle. Triangle can be put isometrically on the Euclidean plane. So you put them isometrically on the Euclidean plane. This is the distances in the Euclidean plane, and now you take the middle point between two points of the 3. Take one middle point, and you look on the distance to the 3rd point. This is the distance in the Euclidean plane. We have simple formula to compute this distance. In cut zero spaces, this distance is at most the distance in the Euclidean plane. So what does it mean? This is for the middle point, but this is true for any point along the geodesic. So in cut zero spaces, any such point, it's actually closer. It's closer or equal to the corresponding distance that you would see in the Euclidean triangle. And what it means is that if you take any geodesic between 2 points in cut zero space and you look on this geodesic from a 3rd point, this geodesic will look like a curved in with respect to the 3rd point, from any point that you're looking at. Okay? This is cut zero spaces. Examples of cut zero spaces, so Euclidean spaces, obviously by this definition, but also hyperbolic spaces and any Riemannian, simply connected Riemannian manifold. But for this talk, the most important thing is that metric trees are also cut zero. This is very easy to see. If you think about any 3 points and you think of geodesic between 2 of them, it gets closer to any 3rd point more than what you see in Euclidean space. This is very simple calculation. So metric tree is also cut zero. And here, use the following observation of Gromov and Kondo independently based on more general, beautiful theorem of Bretowski, not simple theorem, but simple proof, but it puts all these notions in a nice way. I'm not gonna quote Bretowski theorem, but this is one of the, basically a corollary of Bretowski theorem. It says that if you take any graph, you scale it down by the girth, and take the Euclidean cone over it, you get a cut-zero space. Okay, you have to scale it down by the girth, not the diameter. Now the girth is different from the diameter. We'll see it from obviously we know it's different from the diameter. We'll see what it does mean later. Why is that? I'm not going to prove it. Just a slight intuition. I'm going to show you. I'm going to give intuition for two extreme cases. So we know the metric trees are cut-zero. Now, if you take any 3 points, such as sum of the distances between them is less than the girth, then, I mean, it's very easy to see that the induced metric on the 3 points will be a tree metric. So, in tree metric is cut-zero, so the cut-zero condition would hold for the 3 points. And the whole point of the Euclidean cone in this setting is just not to interfere. This property carry over from the cut-zero change the distances, but it keeps this property. What happens if all distances are large? Here you see that the cut-zero is very important. If all distances are larger than the girth, half of the girth, then in the Euclidean cone, what you get, the metric that you get on A, B, and C is actually a star metric, where the 0 is the center of the star metric, and A, B, and C are leaves. Just think about it. You don't need to remember the whole formula, but if you remember, it's just a truncation. I'm truncating at pi. Pi after this scaling just means half the girth. So the distance becomes, all distances become 2 in this setting. And the 0 just be distance 1 from all of them. Again, star metric is a tree metric, which means that it's cut-zero metric, and again, the cut-zero condition holds. In this case, this is just two extreme cases. The rest of the cases are just type of hybrids. But the point is, here I'm actually using, for the second bullet, I'm using the fact that we have this new point origin. I shortcut the distances in the graph of the graph via a new point, the origin of the cone. So this is just intuition. It's not a proof. Now, so I mean, Gromov-Kondor's Bretowski theorem talks about a Euclidean cone over the girth, and we want actually Euclidean cone, over the metric scaled down by the girth, and we want to talk about the problem with the Euclidean cone over the metric with the scaled that is scaled down by the girth. This is not. It does not contain the original metrics. The truncation is real, right? The girth is smaller than the diameter, and you truncate distances, and you get large distortion. So when it doesn't happen? When the girth is roughly the size of the diameter. This is when in high girth graph. This is by the definition of high girth graph, right? So if you look at a random regular graph, they are not high girth. But they are close enough in the sense that there are not many, there are only a small number of short cycles, shorter than much shorter than the diameter. So for this talk, we're just gonna ignore the fact that the random regular graph have a small girth, and let's think about the girth as being the diameter, but the actual argument here is lengthy and technical, and it's a good reason to just skip it. So let's ignore it, and continue on. So now it's, so we saw what is nice about barycenter from our point of view. They have a natural notion of barycenters. And barycenters here just mean a point that's a barycenter of probability. In this, I mean, for our setting, barycenter will be for any probability distance, for any probability distribution over this space. The center of mass is a point that satisfies this inequality. What does it say? This is a point, what I call CM of U. U is a probability distribution. We have a point CM of U such that for any point X, if you want to see, if you look on the distances from X to the distribution, if you look on the average square distance from X to the distribution, this is at least as the distance from X to the barycenter, to the center of mass, and from the center of mass to the distribution. So if you want to go from a point X to a distribution, it's cheaper to go, instead of going directly, you should go via the center of mass, and from the center of mass, you should go to the distribution. In Hilbert space, this inequality is just equality, right? If you think about it, this is what the center of mass is just the average of the distribution, the expectation of the distribution. In cat-zero spaces, we have this inequality. Why this is why it's true why it's true. So the proof for general distributions is it's a nice proof. It's not complicated, but it's standard. I mean, it's in textbooks. For 2 points, it's actually basically the definition of the definitions that I gave you for cat-zero space. So what we want going to prove in 2 points. So we have now point X and a distribution over 2 point U1 and U2. And this inequality that you see here basically says that the blue is larger than the red, is at least the red, right? This is what is written here. The red point is the center of mass. Now, what you need to do is just to write it down in Euclidean plane. This is a green line. In Euclidean plane, this is actually equality. This is what I said before. And by the definition of the cat-zero, the distance between X and the center of mass is at most the distance you see in the Euclidean plane. So it's just smaller, right? And if we combine these two inequalities, this is what you get. So just basically the definition of cat-zero for 2 points. This is why you have this barycenter. Now I'm going to will become more vague. Basically, we have barycenter. We can now define martingale, the general abstract notion of martingales. So what is martingales? I'm not going to define martingales, but basically you have a filterization. You have a sequence of a probability space, which refinement of each other. And the point is that the average the average in the step of n plus 1, if you condition on the filter on the space in n is equal to the step n martingale. This is a regular definition of martingale.
It's unique.
In cat-zero, yes. Yeah, but this definition actually you can just define barycenters very abstractly. It's abstract nonsense in this sense, this definition. I just define the Mn to be a center of mass of Mn plus 1 with respect to Fn. Instead of taking the expectation, I'm replacing the expectation with the abstract notion of center of mass. And in cat-zero, where the center of mass is unique, we actually get this martingale inequality, which is called Pizier-Martingale cotype inequality. This is its name. It says that if you look on the martingale, then the distance between the beginning and the end of the martingale is at least, the square distance between the end and the beginning is at least the sum of the martingale difference squared. Again, in Hilbert space, this is just equalities, basic equality of basic property of martingales. the nice thing here is that this is actually can be defined, and although martingales in this abstract setting is very different. I mean, they don't have many properties they don't have many of the properties that you're used to in regular martingales. Still, this inequality holds. It's called Pizier martingale inequality because Pizier used it to characterize the uniformly convex Banach spaces that I talked before. Very nice work. But the proof that cut zero have this property is basically one line. It's induction on the definitions that on the very central inequality that I just showed in the previous step. This is one line proof. I mean, there's no just really definitions, and there's not much more than that. Now that we have this martingale inequality, here again, it becomes very vague. You can use it to prove another inequality, this time on reversible Markov chains. And it's an inequality that I didn't even write it down because it's even more complicated and it's very long. I don't have the time for it. But basically, it's an inequality that says that if you take any reversible Markov chain in your space, and you start from this steady state distribution, you take t steps, and after t steps, the average square distance is at least as large as t times the average square distance after one step. This is not true, as I said it, but it's at least the gist of the inequality. And from this inequality, I mean, random walks on symmetric metric spaces and on symmetric random walks and power of graphs are very closely related. It immediately implies the decay of G. And this is, I mean, why we used all this machinery, I guess. Some remarks. So this is just an expander with respect to random regular graph. The whole subject is about we have it, that this talk is very specific to this class of random regular metric space of random regular graphs, which is just very small result in basically C of. We don't know a lot about expanders in metric spaces, and I mean they are even with directly related to this talk. So we saw these cut zero spaces in which that we construct over a random regular graph, and we show they are expander with respect to them. But we don't know whether there is expander with respect to all cut zero spaces. We don't know what are the criterion for having expander with respect to given Banach space. We suspect that this is the last point is the right criterion. I mean that if a Banach space there is expander with respect to a Banach space if and only if it doesn't contain finite dimensional L infinities, but we don't know how to prove it. There is a whole question about random regular graph. How to prove that they are expander with respect to some metric spaces? We don't beyond what is currently known about edge expansion and the trace method which work in L1, L2, and can be lifted to any LP. We don't have any idea how to prove that random regular graph are expanders with respect to non-trivial metric spaces. That's it.
Questions?
So you mentioned applications to estimating average distances. This DGF work?
Yeah, I mean, if you have this, if this inequality holds, this inequality between the average over all pairs to average over edges, I mean, actually it's approximate equalities, then you can actually estimate, right? From the definition of this approximate equality, if you want to estimate the average over all pairs, just average over the edges, which is linear number of edges. So if you have expander with respect to metric space, you can average you can estimate the average square. Over there.
Any other questions? All right, thank you again.